Here's a pure tone, a single clean frequency, nothing but one cosine wave. Here's another one, a little faster. Now, add them together. And just like that, the two clean tones disappear into one jagged wiggle. This is the puzzle the Fourier Transform was born to solve. So here's the question. Given only the wiggle, how could we ever pull the hidden tones back out? A pure tone is the simplest wave there is. Just two numbers describe it: how tall it stands and how fast it wiggles. That second number is the frequency, the star of our whole story. Crank the frequency up and the wiggle quickens, the pitch rises. Our 2 cycles per second is far too low to hear. The musical A you tune to rings 440 times a second. But real signals are richer. Stack a few pure tones on top of each other, and you can build almost any shape you like. Here's the rub. Going this way, tones into a wave, is easy. You just add. The Fourier Transform asks for the reverse. Given the finished wave, find the tones hiding inside. And that is hard. So hold on to this. A signal is a sum of pure tones. Our job is to read them back out. Take one pure tone, back to our 2 Hz wave. Here's the trick that cracks everything open. Instead of plotting the wave along the line, we wrap it around a circle. Multiply the signal by a little spinning, a rotor that turns at a winding speed we control. As the winding speed climbs from 0, the wave coils around the center, tracing a kind of flower. Think of it like walking out the wave while slowly spinning in place. Most of the time the loops are balanced. They cancel. So here's something to chew on. Is there one special winding speed that throws the whole shape off to one side? Watch what happens exactly when the winding speed hits 2, the tone's own frequency. Every bump of the wave now lands on the same side of the circle. They stop canceling, and the whole flower lurches off center. Back to the winding machine. The one measurement we care about is the center of mass, the average position of the whole wound curve. That's this white dot. Let's keep a running tally. For every winding speed, we measure how far that center of mass drifts from 0 and plot it over here. Now sweep the winding speed up, slowly, and watch both sides at once. There it is. A single sharp spike, right at 2. The winding speed that throws the curve off center is exactly the tone's hidden frequency. Now the real test. We feed in the messy chord, 2 and 3 Hz tangled together. Before we turn the crank, where do you think the spikes will land? Sweep again, and the chord confesses. 2 clean spikes. 1 at 2, 1 at 3. Exactly the tones we hid inside it. So here's the engine of the whole idea. The spikes of the winding average mark the frequencies hiding in the signal. That picture was a touch too clean. Let's interrogate it. 3 times. 1. The center of mass is a point in the plane, not just a height. It also carries an angle, a phase. Our spike plot quietly kept only half of it. 2. A real cosine is even-handed. It spikes at plus its frequency, and at minus it. Every peak has a mirror twin across 0. 3. We cheated on time. The true transform runs over all of time. Record for only a few seconds, razor-thin spike smears into a bump. So we amend the rule. Those spikes are really bumps, each carrying a phase, each mirrored across 0. The intuition survives. The fine print just got honest. Let's make the winding average exact. In words, it's the average of the signal times the little rotor. That rotor is Euler's gift. A unit arrow spinning clockwise is just cosine minus I times sine. The winding speed lives right here in the exponent. Averaging over a stretch of time is exactly an integral, divided by the length of the window, t. Drop that 1 over t, and stretch the window to all of time. What's left is the Fourier transform itself. One last thing to ponder. What happens at winding speed 0? When the rotor doesn't spin at all? At 0, the rotor is just 1. So you simply add up the signal. The center of mass collapses to the plane average. Watch the wheel unwind. Here's the whole payoff. Take the chord, run it through the transform, and out fall 2 clean spikes. And they sit at exactly 2 Hz and 3 Hz, the very tones we buried in beat 1. Which finally answers the question we started with. You wind, you watch the center of mass, and you read off the spikes. Solved. But notice the catch. To pin a frequency perfectly sharp, you'd have to listen forever. A sound that lasts only an instant is spread across every frequency at once. So here's the whole story, in plain words. Any sound is a stack of pure tones. To find them, wind the wave around a circle. Watch where its weight gathers. And the lopsided moments point straight at the hidden notes. Remember it as one word. Wind. Waves add up. Imagine winding it round a circle. Note the center of mass. Decode the spike. Which leaves us one last thing to wonder. If a sharper note demands longer listening, how sharp